This is a continuation of the first video on chapter 7 with transistor biasing, but we also introduced PNP transistors. At first glance, the circuit shown above seems like it wouldn't work because the base is at ground. But notice that the emitter is not connected to ground, but instead is connected to negative 12 volts, and this we're going to call VEE. So there is a path for current, and we can begin analyzing the circuit as before. Let VE equals 0 volts minus zero point 0.7 volts, which is negative zero point 0.7 volts. Then the voltage drop across the resistor in the emitter is equal to negative zero point 0.7 volts minus negative 12 volts, which is VEE, and that equals positive 11.3 volts. The collector current is approximately equal to the emitter current, which is 11.3 volts divided by 20 kiloohms. That equals 565 microamps. The collector current causes a voltage drop across the collector resistor, and that equals collector current times collector resistor, which is 565 microamps times 9.4 kiloohms, and that equals 5.31 volts. Voltage at the collector is equal to VCC minus VRC, 12 volts minus 5.3 volts, which is 6.69 volts. Then we say VCE is equal to 6.69 volts minus negative zero point 0.7 volts. That equals positive 7.39 volts. And so this means that this is an active transistor circuit. Earlier we said that a transistor is a three-terminal device made out of two different materials, N, P, N. Now we introduce a new transistor, which is the exact opposite, PNP, and you can see the symbol right below. It's simply the reverse of NPN. So we won't take time with the physics of it. Instead, let us go and learn how to bias a transistor. The first method of biasing the transistor is to take VCC and use a negative supply voltage, in this case negative 10 volts. Let's find voltage on the base by using the same methods as we did before. We'll say that it's negative 10 volts times 2.2 kiloohms divided by 10 kiloohms plus 2.2 kiloohms, and that equals negative 1.8 volts. Now we need to think in reverse of NPN, because in order to find voltage on the emitter, we say it's VB plus zero point 0.7 volts. In other words, negative 1.8 volts plus zero point 0.7 volts, which equals negative 1.1 volt. The collector current is approximately equal to the emitter current, which equals negative 1.1 volt divided by 1 kiloohm, and this equals negative 1.1 milliamp. Negative current means that the current is flowing in the opposite direction of what we think. In this case, it's going from ground up to VCC, but VCC is negative. In other words, it's lower than ground. And so this is indicated by the little red arrow. We continue by saying that VRC is equal to negative 1.1 milliamp times 3.6 kiloohm, which equals negative 3.97 volts. Then VC is equal to negative 10 volts minus negative 3.97 volts. That equals negative 6.03 volts. Once again, we have to think in reverse of NPN by looking for VEC. In other words, VE minus VC, which in this case is negative 1.1 volts minus negative 6.03 volts, and that equals positive 4.93 volts. A positive number between the emitter and the collector means that this is an active transistor circuit. One way to simplify the previous calculations is to take the transistor and flip it upside down and use a positive supply. The red arrow indicates that the conventional current is flowing from VEE down to ground as we would in an NPN transistor. Let's begin as always with the base. The voltage on the base is 10 volts times 10 kiloohms divided by 2.2 kiloohm plus 10 kiloohm equals 8.2 volts. Voltage on the emitter is 8.2 volts plus zero point 0.7 volts, which equals 8.9 volts. Remember, we must always think in reverse. Also, since we're going in the opposite direction of the arrowhead, indicating the diode, we add 0.7 volts. We continue by saying that VRE is equal to 10 volts minus 8.9 volts, that equals 1.1 volts. And then collector current, which is approximately equal to emitter current, is 1.1 volt divided by 1 kiloohm, that equals 1.1 milliamp. Then voltage on the collector is 1.1 milliamp times 3.6 kiloohms, that equals 3.96 volts. Finally, VEC, remember we're in reverse, is equal to 8.9 volts minus 3.96 volts, that equals positive 4.94 volts. Once again, we have a positive number, which means we have an active transistor. Positive and negative voltages are both used to bias PNP transistors, and then we will use them again when we do op amps. So continue reading the book and attempting the problems, although I know they won't make much sense until we do real labs.